In progress.
Howdy, Professor Abdelnour. We are Joe, Holly, and Alyssa, and this is our ergonomic steering wheel Mech 448 project. Starting off with our problem statement, the current Baja cart design is quite cramped, so much so that it restricts the driver's arm motion with the current steering wheel. It's just inefficient use of space in the cabin. So our key objectives are to address the form factor of the existing steering wheel and relative to cabin space, add buttons to the steering wheel to declutter the cabin, and switch to a standard bolt pattern for the steering wheel mount. Our system design specifications are M6 bolt and a 6 by 70 millimeter bolt pattern. The overall wheel diameter must be between 8.5 and 12 inches to make good use of the space. The main material of the plate on the wheel is 6061 aluminum. 4 total buttons with control over the differential, cooling fan for the CVT, diagnostic information capturing, and push-to-talk communication, and it must cost under $250. For our P diagram, not much has changed since milestone 2. Our piece-to-piece, we still have material assembly, wiring, vehicle mounting, change over time, wiring and electrical deterioration from the elements that the Baja cart will be going through, and potential wheel misalignment from hitting something too hard or just wear and tear. Customer usage is to be used in short, high-speed sprints like a race. It is guaranteed to be used. The steering wheel will be used every time every time the cart is used. As far as the external environment goes, mud, dirt, rocks, sand, clay, and pavement are all possible scenarios. Ambient temperature could be extremely cold or quite hot. Uneven terrain, just kind of part of the Baja system. System interaction, we have the steering wheel to the steering wheel mount and the driver to the steering wheel. The input signal is solely mechanical, mechanical from the driver imposing force on the wheel, and mechanical response from the terrain, like rolling over rocks and it would twist the wheel automatically. Control factors are all mechanical as well, the driver and vehicle movement. Error states, anything from noise, rattle, to discomfort for the driver, to failure of the buttons are all possibilities. And our output response is all purely mechanical energy output to the wheels. For our boundary diagram, we ended up just we didn't have anything else to do other than the steering wheel. We didn't mess with any other critical components. Everything is contained to the wheel, and it plugs into existing hardware. So that's kind of what we have here with the plastic polymer wheel grips, the whole steering wheel assembly in the center. Human leads into that, and then environment affects that. And the wheel itself affects the drivetrain by way of the differential. The chassis and frame by way of the steering rack and suspension, and the electrical harness through the ECU, which goes back to the differential for the differential lock. Solid line arrows are physical connections between pieces, and the dashed arrows are electrical connections between pieces.
Here is the Gantt chart that we made for this project to be a timeline for every milestone and the deliverables, and to stay on time for the entire thing. In order to pick the final design, we did a Pew analysis of 3 different design options. Each option was graded on the cost, the size, the durability, the versatility, the grip comfort, and the serviceability. Out of the 3 options, option 2 was the best scoring option, but ultimately we decided to go with a design that is a combination of all 3. This is the CAD for the final design. On the left is the main plate, and then on the right is the grips that will be on either side of the main plate. This is the prototype that we built for the steering wheel. So it uses 3D printed grips, and then the main plate is made out of aluminum. For the FMEA of this design, all of the potential failure modes were tied to the safety of the driver, either in a competition or in test driving the car. And the majority of the potential failure modes come down to either the wheel itself breaking in some way, or some part of the wheel breaking, or the wheel being misaligned or not properly assembled or put onto the car, and what those would potentially lead to. The most severe of those is either loss of control of the car, which obviously is a threat to the driver's safety, or in worst case with the buttons would either be a fire risk, which obviously is a safety risk for the driver, or a loss of communications with the rest of the team on the radio, which is needed so that the driver knows when to come in. They know if there's a crash up ahead where they're driving on course, or any other important information they may need while driving.
The DVP&R, or the Design Verification Plan and Report for our project, covers the major issues of the FEMA by conducting a wire pull test, cold test, vibration testing, and mud, water, and sand tests. Given our limited time, we were only able to complete the vibration cold test at 12 degrees Fahrenheit instead of the expected negative 23 degree Fahrenheit, and wire pull tests, as testing in mud, water, and sand was difficult when the vehicle itself was not drivable. And all the tests that we did run met all criteria. This is our steering wheel function test. For this test, we installed the steering wheel on the hub, turned the wheel left and right to the max. And we're looking to see if the steering wheel stays on the mount to make sure that the feel is effortless and it doesn't take too much effort to turn it. And of course that it's functional and we see the wheels turning on the vehicle. And here's the test itself. For the validation results, the wheel passes the basic function test, where the hub securely attaches to the mount, which is 6 by 7 millimeters. The buttons connect and work properly, and the wheel profile is within a specified diameter. The wheel is easier to handle than the old one, and the wheel takes up less space than the old wheel. For the build plan, we completed the CAD of the steering wheel and the grips. We were supposed to send the CAD to the team sponsor to cut the main aluminum plate. We also 3D printed grips, and then assemble the steering wheel once the grips and plates are printed and cut. We actually were unable to send the wheel to the team sponsor to get cut, so we ended up creating the wheel and hand cutting it out ourselves. But either way, the price was the same, which ended up we were able to find everything in the SAE garage. So we all in total paid $0. For our final cost / design assessment, the cost to produce the wheel itself was about $37.80 per unit, which is not including the wires and fasteners, if we were to not have everything sponsored by the SAE team, which is far below the $250 budget limit that is set by this class. Unfortunately, as I mentioned earlier, the CNC could not be utilized, so we had to hand make the main plate. So everything on the plate that is metal was handmade by us for this model here. From the drivers, we found that the inner buttons were difficult to reach, but the hand grips themselves are comfortable for the drivers. And thank you for listening to our presentation. If you have any further questions, feel free to reach out to us via email.